Okay, let's get started again. I hope you guys had a nice stretch. I hope you were able to get some snacks or maybe get a new pencil, whatever you need to do. I myself got myself some tea, so that's nice. Okay, let's go through an example of the rate limiting step determining the overall kinetics for the overall reaction. Okay, let's look at a real example here. For that's really bad. EX. Okay, let's look at the reaction with our old friend. The reaction between nitrogen dioxide and carbon monoxide. Okay, to form NO gas and CO2. Okay, we've looked at this several times throughout the chapter. Let's look at it in more detail and look at the actual individual steps that go into this reaction. Okay, recall that experimentally, the rate law for this overall reaction ends up equaling K times NO2 squared. Okay, so it's completely dependent on NO2, and it's a second order rate law. Okay, we can tell right away that this can't be a single step reaction. Okay, because this is a second order reaction, we can tell right away that it's not going to be a single step. Okay, because a single step would make a rate that's equal to NO2 squared times CO2, or NO2 times CO. Okay, because if this was the only elementary step that happened, we would know that the rate is equal to K times NO2 times CO. Okay, but that's not the case. That's not what it equals. So we know that this is not a single step. So we want to write out possible mechanisms. Okay, what are some possible mechanisms for this reaction? The first is NO2 colliding with another NO2 to form NO3 and NO. Okay. The second has to consume both of these, or no, it just has to consume NO3 because NO is present in the overall reaction. Where is the overall reaction? Oh man, I went way past. Where am I? Oh, here it is. Okay, NO is right there. So we know that we have to consume NO3 in the second step. So let's react NO3 with the thing that's left, carbon monoxide, to form NO2 plus CO2. Okay? In this case, we have a very slow reaction. Oops. And this is a very fast predicted reaction. Okay? That means that because this first one is so slow, the overall predicted rate law is determined by rate limiting step. Okay? So we'll say step 1 must be slow or slower than 2, and must be rate limiting step. Okay. From this, we can form the overall rate by simply looking at step number 1 because it's an elementary step. So then the rate from this would be equal to K times NO2 squared, which is exactly what we had up above. Okay, this is exactly the rate that we had from above. Whoa, what the heck just happened? I'm going to erase this so that it's more clear. This is exactly the rate that we had from above. So we know that this is probably a pretty good representation of the mechanism that's happening here. Okay, so this is consistent with experiment measured in real life. So this possible mechanism makes a little bit of sense. Okay, makes a little bit of sense. And the way that this looks in energy space, whoa. Turns out I'm really bad at drawing vertical lines. I don't know what that says about me. So let's look at the energy versus the reaction progress. Okay, so same as we looked at before. We have the reactants on this side, and we have the products on this side. Okay. In this case, since we have two steps, we have actually two activation energy barriers that we need to overcome before we make it all the way back down to the products. Okay. Now, interestingly enough, in the way that I've drawn this, the activation energy for the first step is much greater than the activation energy for the second step. And then the overall delta H is negative here. So this is the delta H for the reaction is the difference between these two. Okay, so because this delta A for the first step is so much larger than the delta A for the second step, we can say that this graph here is a pretty good representation for the reaction steps we've drawn above. Okay, we have a very slow process for the first step and a very fast process for the second step, relatively. If you recall back from the description of the rate constant, K is equal to A times e to the negative EA over RT. K is large, or K is fast, when EA is small. K is small, or K is slow, when EA is large. So we can see that for the larger activation energy, and it kind of makes sense from a practical perspective if you just think about it, the larger the energy barrier that you have to overcome, the slower the reaction will be. Okay, so this is a reasonable way of thinking about the two reaction mechanisms written above. Okay. All right. For a proposed mechanism to be valid, number one, the elementary steps must sum to the overall reaction. Okay. Number two, the real life predicted, or the rate law, not real life, rate law predicted must be consistent with the experimentally measured rate law. Okay, so the predicted rate law must be consistent with the measured rate law. For our two steps above, if we add them together, steps 1 and 2, so we have NO2 reacting with NO2 to form NO3 plus NO. If we add that with the second line, which is NO3 gas, reacting with CO gas to form, what am I forming here? NO2 plus CO2. Okay, if we add these together, we find that the NO3 cancels out, boom, boom, And we also find that one of the NO2s cancel out. Okay, so we're left with the overall reaction of NO2 plus CO goes to NO plus CO2, which is the original overall reaction that we started with. Okay, so since that sums to the overall reaction, it satisfies the first rule, and since the predicted rate law is consistent with the measured rate law here, that means that this possible mechanism is a valid mechanism. Okay, so this is a valid mechanism. Okay, and there are certain ways that we can kind of distinguish between different commonalities that happen within chemical reactions. Okay, so we can have a mechanism with a fast initial step. Okay. Okay, we can have mechanisms with fast initial steps. That means that the rate law that we predict from these elementary steps may contain intermediates. Whoa, what does that mean? That means that when you form the rate law from one of these fast elementary steps that actually form an intermediate, you can end up having an overall rate law for the overall reaction being proportional to the concentration of an intermediary, an intermediate. If this happens, in this case, you need to express the intermediate, the concentration of the intermediate, with the reactant concentrations. Okay? We don't want to actually leave the intermediate in the rate law itself. It wouldn't make any sense to have that. So we want to express the intermediate concentration using reactant concentrations. Okay? So for example, if we have a reaction between hydrogen gas and NO gas to form 2 waters and nitrogen gas, the rate law that we measured experimentally, so the experimental rate law, is equal to the rate constant times hydrogen times NO squared. Okay, so this is the experimental. A possible or a proposed mechanism, I don't know if you guys can hear my kids playing outside. I have the window open, and the sound might be coming in, so you might be enjoying my kids just as much as I am. That may or may not happen quite often during this period of online lectures, to be honest. Okay, so the proposed mechanism we have is step number 1. We react 2 NO gas molecules together with some initial rate constant, K1 we'll call it, to form N2O2 gas. Okay, this is a fast reaction. Second step would be the reaction of hydrogen gas with N2O gas oh, N2O2, sorry, with that intermediate. This is K2 to give H2O and N2O gas. This is a very slow reaction. And then finally, the third step would be reacting N2O with H2 to form nitrogen gas and water. And this is, again, quite fast. If we sum these together, we find that, let's do some canceling out here. So we can cancel out N2O2, N2O2. We can cancel out some N2O and N2O. And I think that's it. Yeah, that's it. So we end up with 2NO gas plus 2H2 gas goes to 2H2O gas plus nitrogen gas. Ooh, that's bad in there. Okay, that's the overall reaction. That sums to what we initially started with up top, so that checks out. Now we want to see if the rate law that's predicted by this intermediate step here is the same as what we've seen experimentally. Okay, that's what we want to check now. So look at the rate law for the slow reaction. Second step is the slow reaction. It's the rate determining step. And the rate that we would predict from this just by looking at the reactants would be, so from step 2, the rate law would be rate is equal to K2 times H2 times N2O2. Okay, now we've run into the problem that we've mentioned above. We have a rate for this step. The slow step is proportional to an intermediate. So this cannot be consistent with experimental rate law, okay, because it contains the intermediary. So what we need to do is we need to express this intermediate in terms of the reactants, okay. In step 1, we take 2 NO gases and we convert them into NO2. Okay, so that's step 1. 2 NO goes to 1 N2O2, like that. And this is a very fast reaction. Since it's fast, it will proceed until it is at equilibrium. Okay. Basically what this means is that enough N2O2 has built up to drive the backward reaction. Okay, and so what that means is we have, instead of just a forward reaction, we have 2NO going forwards and backwards with N2O2. Okay, so it's going to reach an equilibrium where this one on top is K1 and the one going backwards, we'll call it K minus 1. Okay, so that's the backwards reaction. At equilibrium, K1 is equal to K minus 1. The rate going forward is the same as the rate going back. That's why it's at equilibrium. The concentrations of N2O2 and NO don't change in time when it's at equilibrium. Okay, so we can express the forward reaction, or the forward rate law, as rate equal to K1 times NO Hold on a second, I think my battery died in my pen. Okay, let's see if this works. Nope, it's not working. Okay, something's weird. Hello? Oh, okay, here we go. For some reason I got clicked out. I don't know why. So the rate for the forward reaction is K2 or K1 times NO squared. And the rate for the backward reaction, what the heck? Something's going on really weird with my pen here, guys. You see this? It's deleting my stuff. What's it doing? Huh. I don't know what's going on. Technology, right? What is going on here? I don't know. I don't know what's going on. Okay, I think I'm going to have to pause this here. This will be all we'll get through today. We only have a tiny little bit left of chapter 14. So we will continue to keep the homework due on Monday next week. We just have a little bit left. So work on this over the weekend. And we will finish up this little bit of kinetics on Monday morning. And you should have plenty of time to finish any questions that we haven't covered yet by the time the homework is due. And in that time, I'll figure out what's going on with my pen erasing all of the bits. I don't know what's going on. It has to be something to do with technology. It's definitely not a problem with the user. It's most likely a problem with the software. You know that is probably not true. I'm doing something weird and I know it. Anyway, I hope you guys have an excellent weekend. If you need anything, shoot me an email. A couple of you have already shot me an email regarding the homework. So if you are at all confused about it over the weekend, please feel free to email me. I will have, or I will be able to respond to you over the weekend by email. Okay. So yeah, with that, take care. Have a good weekend. Happy studying, happy homeworking, etc., etc. All right, later.